Okay, so today we're going to graph based off of sine and cosine values on the unit circle. So let's refer back to the previous chapter where we had completed a unit circle, and we're going to use these values, remembering that cosine is your x coordinate and sine is your y coordinate, and we're going to complete the table that's in our node sheet. So we filled in the column for the y coordinates at all of these angles, and I'm going to start at 0, 0. We're going to plot that. Now, if you notice, your highest value goes up to 1 and your lowest value goes up to -1. So I'm going to mark that on my graph. And I'm going to also mark -1/2 and +1/2. For pi over 6, that's a third of the way to pi over 2. We're going to go up to 1/2. And for pi over 4, that's exactly halfway to pi over 2, we're going to go up to √2/2, which as a decimal is 0.707, and so we can draw our best estimate of where that location is. Then at √3/2, the x-coordinate would be pi over 3, and that would be at 0.86. And our highest point on the sine curve would be at pi over 2, 1. So as you can see, it's starting to make almost a parabolic shape, but we call it a sinusoid graph. So I'm going to keep moving along, and at 2 pi over 3, we're going to go back down to √3/2, which is at 0.86. At 3 pi over 4, we're going to go to √2/2, which is at 0.7. At 5 pi over 6, we get to 1/2, and then at pi, we get to 0. So as you can see, it's symmetric, with pi over 2, 1 being the highest point of that portion of the sinusoid graph. All right, and then from pi to 2 pi, all the values are negative, but it essentially repeats the same pattern. So at 7 pi over 6, we have -1/2. 5 pi over 4, which is halfway between pi and 3 pi over 2, we are at about -0.7. At 4 pi over 3, we're at -0.8. And at 3 pi over 2, we are at -1. And then we should notice that it will be symmetric until we get to 2 pi, and we're back at the x-axis. All right, so here is one period of the sine function, and you will get very used to this graph, and we'll be elaborating more on this graph throughout the rest of the chapter. But you'll notice that your roots, or your x-intercepts, are at 0, pi, and 2 pi. All right, so as you can see, I've filled out the cosine, or x-coordinates, of all these points on the unit circle, and we're going to create the same graph, but for cosine. So you'll notice that the highest value is 1, and the lowest value is -1, and we're going to make markings for -1/2 and +1/2. So the cosine function starts at 0, 1 on the y-axis, and then goes to 0.86, 0.7, 1/2, and then at the pi over 2 angle, it goes down to the x-axis. And then we start to go into the negative region. So at 2 pi over 3, we have -1/2, and then we have -0.7, -0.86, and then -1. And then it continues to be symmetric, and this gets us into the third quadrant in the coordinate plane. So we are at -0.86, -0.7, -1/2, and then at 3 pi over 2, we're at 0. So if I draw in some of the cosine curve, you'll start to see that it looks similar to the sine curve, but just shifted over a little bit. All right, and then continuing for the fourth quadrant angles, we've got 5 pi over 3, we have 1/2. At 7 pi over 4, we're at 0.7. At 11 pi over 6, we got √3/2. And at 2 pi, we're at 1. So that is one period, or one repetition, of the cosine function. So if we were to refer back to our completed unit circle and we look only at the y coordinates, it goes from 0 to 1, and then the y coordinates go back down to 0, which is what's shown in our graph. So it goes up, and then it goes from pi over 2 to pi, it goes down to 0, and then we get into the negative sine values, and you can see that all of our sine values are negative into the third quadrant and then continuing into the fourth quadrant to get back to 0. And if we were to continue to rotate around 2 pi and continue to do this over and over again, we would just repeat the same cycle over and over again. So this is why these are called periodic functions, because every 2 pi, or 1 period, it will repeat the same exact values of sine or cosine. And that even if you were to add 1 full period, you will still get the same original function. Our cosine function also has the same period. Let's take a look at our completed unit circle, this time for cosine. So if we were to take a look at all of the x coordinates, you'll notice that they go from 1 to 0, and then they start to go into the negative range from 0 to -1. And then on our graph, we go from 1 to 0, and then go into the negative range from 0 to -1. Then in the third and fourth quadrants, they go back to 0, and then go back up to 1. And you could see in the graph, in the third quadrant, they would go back up to 0 and then back up to 1. So sine and cosine both have a period of 2 pi. Another new vocabulary word is amplitude, which is basically the height of the graph, and the amplitude is 1. If you look at the minimum and the maximum of our graph, find the difference of those, and then divide by 2, you'll see that it's 1. So our highest point is 1, our lowest point is -1, 1 minus -1 is 2, and then divide by 2, and you get 1. Related to that, the range goes from 1 to -1 for both sine and cosine. And because we can have as many degrees or as many radians in an angle as possible, we can go to -infinity and +infinity for our angles, and we could extend our graphs infinitely to the left and infinitely to the right. All right, so let's take a look at the concept of even and odd functions. The sine function starts off at the origin on our graph, but let's look at one particular angle as an example. So the angle pi over 4, if we were to look at the y coordinate, is 1/2. And if we look at negative pi over 4, the y coordinate is -1/2. So if we take the opposite of the angle, the y coordinate also is the opposite. So these are the trig functions that are odd functions. And then cosine is considered to be an even function, because if we were to take a look at the cosine or x coordinate of that pi over 4 and negative pi over 4, notice that they're exactly the same. So cosine of negative of an angle is the same as cosine of positive of an angle. That is considered to be an even function. The other note that's on here is that the inverse of sine, if we were to know that the sine value is 1/2, there is only one unique number or one unique angle within the range of negative pi over 2 to pi over 2 whose sine would be 1/2. If we were to look at cosine, however, if we were to take the inverse cosine, it's not between the range of negative pi over 2 to pi, it should be in quadrants 1 and 4. Instead, we need to look at quadrants 1 and 2, because the cosine of those two angles are exactly the same. So if we want one unique solution, instead of looking at quadrants 1 and 4, we need to look at quadrants 1 and 2. So if I were to know that the cosine of an angle is √3/2, that is only pi over 4. So even that same reference angle in the second quadrant would give me an x coordinate of -√3/2. And so that would not work. It would only be that one singular angle of pi over 4. All right, so let's take a look at this Desmos animation. The blue dotted circle represents the unit circle on a coordinate plane, with the green dot being at the origin. And we're going to change the angle, which is the blue dot, to different angles. We're going to increase it, and we're going to go from 0 to pi over 2. That's covering the first quadrant. And notice that green line, which represents our sine value or our y coordinate, is tracing out the path of our sine curve. And if I go down to pi, then that gives me the sine curve that we have created. And I'm going to continue into the third quadrant and into the fourth quadrant. So now I'm going to zoom out a little bit so that I can show you a repetition of this sine curve. So I'm going to continue rotating around the unit circle, and you'll notice that our sine curve continues to draw itself in the exact same pattern and ends up, now we have 2 repetitions of the sine curve. All right, so this time we're going to take a look at the cosine curve. As we go from 0 to pi over 2, the purple curve is drawing out our cosine function as we've seen on our table and our hand-drawn curve. So there's one period of the cosine curve. So now I'm going to zoom out so that it shows you going around the unit circle one additional time. And now we have 2 repetitions of the cosine function. In these examples, they want you to identify the amplitude and the period. And we don't know if these are sine or cosine curves, but it really doesn't matter. So when we look at the amplitude, we are looking for the highest point on the graph and the lowest point on the graph. And you could see that the highest and lowest points are 1 and -1. So that when we find the difference between that, that gives us 2 over 2, which is equal to 1. To determine the period, you want to look for 1 repetition. So you can start wherever you'd like. If I wanted to start here, I'm going to draw until I create 1 repetition of the graph. So now I'm going to see if I can replicate that and how much along the x-axis then have I traveled each time that I create that same picture. So from one point to the next, just look at how far you've traveled. Now I know it's not labeled, so we can assume that this is halfway in between, and it's from -1 to +1. So my period, the distance from the beginning to the end of 1 repetition is 2. So if you want to look at the red graph, it goes from 1 to 3. That also has a period of 2. And the purple graph goes from 3 to 5. So again, a period of 2 for that one. So let's try the next one. The amplitude is your highest point to your lowest point, which I can see from the y-axis. It goes up to 3 and goes down to -3. So that gives me 6 over 2, which is 3. Another way that you could look at the amplitude is to find where is the middle, and it should go up the same amount as it goes down. To determine the period, again, we're going to start at any particular point. So let's say I start here. I want to create 1 graph that then repeats itself numerous times. And then once I figure out what the graph looks like and where the beginning and end are, then we can count along the x-axis. So let's take a look at the green one. It goes from 8 to 16, so that has a period of 8. And I could verify that with the red one. It goes from 0 to 8, and this purple one goes from -8 to 0. So the period is 8. In number 3, it tells me specifically that we are dealing with a sine function, and so we have to think of this as a sine function. And so we know that our sine function starts at 0, 0. And according to just y equals sine of x, no manipulation to the equation, it should have a period of 2 pi. And every time it repeats this same picture, right, it goes upwards and then downwards, every time that it repeats that pattern, it should go an additional 2 pi. So I like to label that first, and then I can identify some of the other points. And on the left side, I would have -2 pi, -4 pi, and it doesn't quite get to -6 pi in this picture. All right, so one of our coordinates we've got already. That's 6 pi, 0. That one's easy. And then some of these other ones are not at the end of a particular period, but in between. So we know that to go from 2 pi to 4 pi, right in the middle, should be 3 pi. So then halfway in between, and the lowest point on that part of the curve should be at 3.5 pi, or better known as 7 pi over 2. And the lowest point on the sine function would be at -1. Even though we don't have the y-axis labeled, we know that the regular sine function goes up to +1 and down to -1. So we know that this point over here goes up to +1, and we just have to figure out what's the x-coordinate of it. So if it goes from 0 to -2 pi, halfway between has to be -pi, and halfway between -pi and -2 pi is -1.5 pi, better known as -3 pi over 2. So this coordinate is -3 pi over 2, 1. And then our last point we know that it intersects the x-axis at every pi. So this must be negative 5 pi. So the ordered pair here would be negative 5 pi comma 0. For number 4, we're going to refer back to the graph that we just drew in number 3. Look at the interval from negative pi over 2 to positive pi over 2. I know that this point is at pi, and halfway between 0 and pi would be pi over 2. And this would be negative pi over 2. So the question is, what's happening between negative pi over 2 and pi over 2? Those values are going upwards, so that would be considered to be increasing. In problems 5 and 6 now, we're looking at a cosine function, which we know begins at 0, 1. So this highest value is 1. This lowest value would be at negative 1. And we know that the period to repeat one picture of this graph would take 2 pi. So this tick mark on the x-axis would be 2 pi. This one would be 1 pi. And if we were to go halfway in between, that'd be pi over 2 and 3 pi over 2. So let's identify the black points that are drawn on here. So the easiest one I would say is this pi comma negative 1, because we know that's the lowest point of our cosine function. And then since we're going pi over 2, pi, 3 pi over 2, 2 pi, this is adding another half pi. So that would be 2.5 pi. And that's better known as 5 pi over 2 comma 0. All right, and then our last one, we know that the highest point would be at 0, 1. Our lowest point, we would be going every pi. And to get a full rotation of the cosine function, that would get us to negative 2 pi. This x-intercept would be halfway between negative pi and 0, which would be negative pi over 2 comma 0. For number 6, we're going to use different methods to solve cosine of x equals 0.3. In the first one, we're going to use the graph in number 5 to estimate the root of the equation within the interval of 0 to pi over 2. So we're only going to look at this portion of the curve from 0 to pi over 2. And we want to know, when would the cosine value be equal to 0.3? Well, it's a little hard to estimate on this tiny graph, but here would be 0.5. So 0.3 might be there. So if I were to figure out where that is on the graph, all right, now we want to estimate that. So we're going to use a decimal approximation. Pi over 2 is about 1.571. If this were 1.571, I'd say this is maybe something like 1.2, 1.3, somewhere around there. So we're going to give our answer as x is approximately 1.2 or 1.3. So for part B, we need to use our calculator and verify that it's first in radian mode. So make sure that's highlighted. If it's not, press enter and then quit out of there. And then we're going to do what's called the inverse cosine. So second cosine will get you to that. And we're going to type in our value that we have cosine of x equal to. And that gives us our angle in radians of 1.2661. All right, so Parts C and D both use a reference angle, and we're going to draw a coordinate plane to find another solution within the interval of 0 to 2 pi that gives us also cosine of x equaling 0.3. So we know that if we were to rotate and make a reference angle of 1.2661, and our x coordinate is 0.3, we don't care what our y coordinate is. In order to get that same exact x coordinate, we need to be in quadrant 4. Where this would have 0.3 as my x coordinate and then some y coordinate. So it would create that same reference angle, just opening downwards to create that angle in the fourth quadrant. And so to get there, we could go almost 2 pi, but we would stop short. So we would go 2 pi, but we would subtract off 1.2661. And that gives you another angle. So that angle is 5.0171. Now they want us to find all roots of the equation cosine of x is equal to negative 0.3. So in order to get a cosine that's negative, we need to draw into the third or fourth quadrants. So it would have that same reference angle of 1.2661. So in order to get into the second quadrant, I would stop short of pi. I would subtract 1.2661 from pi. And to get into the third quadrant, I would go past pi, so I would add on 1.2661 beyond the pi. So we just need to figure out what those two values are. All right, so if we add and subtract 1.2661 from pi, we get 4.4077 and 1.8755. So remember, if you have any questions, make sure you ask your teacher about any of these example problems or definitions. Have a nice day.